So I will talk about diffuse gas in galaxies from kiloparsecs to milliparsec scales. Please join me on this trip from galaxies to filaments. Okay, I'll do that. So what you see here is, so I will talk about H1. H1 is, le pointeur fonctionne, merci. H1 is neutral atomic hydrogen, a proton and an electron. I will talk about H1. The observable I will show you, most of the slides you will see, are coming from the 21 centimeter emission line of hydrogen detected in the radio since 1951 and observed in the Milky Way and in nearby galaxies extensively. This emission line, the integral of the line is proportional to the column density, so it gives you a sense of how many neutral hydrogen atoms you have on the line of sight. And the line width of those lines gives information about the thermal broadening and the turbulence broadening of your gas. What you see here is M81, and a combination of stellar, so optical images, you see stars and the bulge of the galaxy where you have star formation. And in blue, it's the H1. It's the atomic gas in this galaxy. You see that it extends far from the stellar disk, but is also present in the halo, and you can even see interactions with partner galaxies or neighborhood galaxies. So it's a powerful tracer to look at the context of star formation. So this is another example, a very recent example of NGC 1512. You see the stellar emission of that galaxy and with its little neighbor NGC 1510. And this is at the same scale, the H1. In fact, if you look at the profile of surface density, the stellar disk is right here, so there's just stars in the middle here. But the H1 extends more than 10 times the stellar radius in this galaxy. This is a large extent of H1, but it's not unusual to see H1 disks that are much larger than stellar disks. In our own Milky Way, if you look at the full sky, this is the H1 emission over the full sky. So we live in a galaxy, so there is the galactic plane here, and there's also a lot of emission above and below that galactic plane. I will tell you a bit more about this later. But now let's talk first about the structure of the Milky Way. So I told you that the 21 centimeter emission line was detected in 1951. In fact, when you observe this line in this area of the galactic plane, you see a quite complex spectrum that extends for almost 200 kilometers per second in velocity, with many emission components along the line of sight that just represent the rotation of the Milky Way, all the different spiralones that you cross along that line of sight, and this is the structure you see. What's interesting is the spectrum below. It's an absorption spectrum, so it's a nearby line of sight that crosses a galactic radio source that is in the back. That is very strong, and when you observe the H1 in front of that radio source, you see the gas in absorption, and it's a very different profile because this is just cold gas. The cold gas absorbs much more efficiently than warm gas, so in absorption you see the cold phase of this atomic phase of the atomic H1, and here you see the total. It's all the temperature and the multi-phase of the H1, so the warm gas and the cold gas. This was detected very early in the 50s, and so it led very rapidly to the bistable or two phases theory of the H1 that I will describe. In fact, the cooling and heating processes in the H1 leads to in this pressure density diagram. Here I'm showing a numerical simulation of that effect. Of the H1, and how in the H1 you have in fact a very diffuse warm phase at about 6,000 Kelvin, and inside that you have clouds that are formed by the thermal instability, which is the result of the specific cooling and heating processes of the H1. And those clouds have density of about 100 and a temperature of about 100 Kelvin. So you have cold and dense clouds immersed into a very diffuse density of about below 1 per cc and 6,000 Kelvin. And in this pressure density diagram, you see those two phases as this is the warm phase here, and this is the cold phase here. And there's quite a lot of gas in between, as you can see here. It's just because this is a turbulent box, and there's gas flowing from the warm to the cold phase constantly. Typically in the ISM in the Milky Way, when you look at a volume of about 50 parsec nearby to the sun, there's about 30% of the mass that is in this cold phase and 70% of the mass in the H1. And because of the difference in density, this cloud phase is occupying a very small volume. In fact, it's less than 1%, or about 1% of the volume is in those clouds. I cannot resist showing this video that Shmuel Gaili showed me last summer. This is a pressure density diagram of a silk simulation. So it's the group of Stephanie Walsh. And what you see is, as time goes by, there are tracer particles in the silk simulation. It's a multi-phase simulation with stellar feedback forcing, supernova feedback. So you saw, so this is the CNM branch. So you have cold gas that is transiting from the warm phase to the cold phase here, and those clouds become self-gravitational at some point. They form stars, and then stellar feedback happens, and then they go back to the warm phase and come. So you really have a conveyor belt of H1 here. What you need to, I'm not sure I fully agree with that representation, but this is giving you an idea of what's happening. The important part here is I think the fact that the CNM structures are long-lived. They stay there for millions of years. So they're not just fluctuations in a turbulence density fluid where in a dynamical time they will go away. Once they're formed, they stay there for a long time. And even if they're not self-gravitating. So yeah, and those clumps are in fact subsonic or transonic. Those structures inside them, the turbulence is very close to transonic, to a Mach 1 or 2, Mach 1 or 2, and it's the same thing here. In the WNM, the Mach number is around 1 or 2. So you have a system here that is not highly supersonic. In fact, it's not supersonic turbulence, but it's creating large density variations, like what you would expect from a supersonic fluid. In fact, the power spectrum of those two components are very different. So this is the power this is a compensated power spectrum. So this is close to Kolmogorov compressible. You would expect for a compressible isothermal fluid at 8,000 Kelvin, and here it's a much shallower spectrum because there's a lot of small scale features. And as I said, well, this is similar to supersonic turbulence. As you increase the Mach number, you would get shallower and shallower power spectra. It's the same kind of idea, but here it's just the thermal instability that does the trick. So now we're doing, many people are doing simulations like that, and it's just, this one is great by Fielding in 2022. Just I wanted to show you is these are just perpendicular to the board on a specific line of sight what the temperature and the density looks like. So you see there are jumps in temperature and density on very small scales. These are the CNM clouds I'm talking about. Okay. In the Milky Way, let's go back to the Milky Way. Those diagrams are very instructive, I think. This is the surface density of the gas as a function of galactocentric radius in the Milky Way. The blue line is the molecular gas, and the stellar disk is very close to that as well. It goes down at about 6 kiloparsec in galactocentric radius. It starts to decline. The H1 goes way further. It has a much larger extent, like in the galaxies I showed you earlier. So there's quite a lot of H1 in the outer galaxy. And what's also important to know is that the disk is flaring. So the scale height of the H1 is about 100 parsec in the inner galaxy, but then it goes to kiloparsec scales in the outer galaxy. and the midplane density goes down from about 1 to 10 to the minus 3 and 10 to the minus 4 in the outer galaxy. So that's the picture of the Milky Way we have now. What is a bit surprising is this work by John Dickey in 2009, where he looked at absorption of H1 just to get the CNM in the outer galaxy. So if you can't read this, this is going from about 8 kiloparsecs to 25 kiloparsecs in galactocentric radius. And the quantity that is plotted here is proportional to the amount of gas that is in the cold phase. And it's constant. It's almost constant to a level that is around 15 to 20%. So I still have a hard time reconciliating this result with those facts that the surface density is plunging. There's not the surface density plunging, the midplane density is plunging, and also the flaring of the H1 disk. I don't understand how clouds can still be formed in a medium that is so diluted. I think this is still a question, an open question, but it might be interesting to understand it. And numerical simulations are not able to reproduce this for now. This is a very good work looking at the correlation between molecular gas and numerical simulation in a spiral disk by work by Smith et al. And looking also at the CNM, the cold atomic gas. There's a very good correlation between H2 and CNM, and there's no extended CNM disk like what I showed you in the Milky Way. So we're not able to reproduce this right now in simulations. I wanted to show you the Magellanic Clouds, and Bruce alluded to this and showed this in his talk just before me. What you see here is that's a galaxy. It's the Large Magellanic Cloud. This is 1 kiloparsec. In color is the H1. It's the atomic gas, and in contours is where the CO is. We are right now with ASCAP mapping this whole galaxy at high resolution, and I can tell you there's plenty of CNM everywhere. So not only where there is molecular gas, there's CNM in all those structures, and what's very striking to me is that there are very big holes in this structure, in this galaxy, that I'm not sure it can be only attributed to stellar feedback. So understanding how this structure can happen at the scale of a galaxy, I think is very important, and trying to understand how this gas forms clouds in regions where stellar feedback is not important is a key element, I think. Yeah. So now I'll talk a little bit about the high galactic latitude stuff. So here I just looked at, this is a 21 centimeter emission spectrum that is taken around here. It's much simpler, as you can see. There's only a few components, and this is because the gas you see here is mostly coming from the solar neighborhood. There are some clouds here that are in the galactic halo, that are away from the galactic plane, but most of that is just the layer of the spiral arm the sun is in. So it's just matter that is around us. And so it's an opportunity, looking at that is really an opportunity to look at the fluid on very small physical scales, because those clouds are about 100 parsecs away. And they are relatively simple. So I'm showing this because I think this is an amazing view of the, now we are able to see the environment of the sun from above. 5 minutes, okay. This is obtained from dust, extinction using Gaia. So you have measurements of star distances, and we can measure extinction on each stars. We have millions of stars, and we can reconstruct in three dimensions what is the structure of the ISM in the solar neighborhood. Well, it's 2 kiloparsecs each side, so it's kind of a big piece of volume. And what you see here is that there's quite a lot of holes and regions of faint where there's not a lot of current density. We know that we are in the local bubble. We know that there were supernova that ejected and created that bubble. But there are also large structures where there's no gas. And most of that is H1. We are in a place in the Milky Way where molecular gas is a subdominant quantity. Well, it's mostly H1 in the solar neighborhood. So what you see here is mostly the structure of the H1 gas.
Is it a horizontal plane?
It's like if you were above the galaxy. You're looking from above the Milky Way. Yeah. Okay. I have to rush to go. So just want to show you that we are able now to separate those phases from emission data, doing analyzing the spectral cubes of the 21 centimeter emission, using techniques to separate narrow lines from large lines, from wide lines. And we are able to make maps and cubes, in fact, of what is coming from the warm phase and from the cold phase. So this is just a piece of sky at high galactic latitude, a very random piece of sky where we have done this exercise. And we are finding, like in the numerical simulation, that the power spectrum of the WNM is steeper than the power spectrum in the CNM. The CNM is occupying a small fraction of the volume. It's mostly filamentary. And so we are starting to be able to do this kind of thing. And estimating the CNM fraction is now being an industry. We are really want to know where CNM is forming, where in which conditions. So we are studying regions, loops close to the sun or clouds in the galactic halo. And we see large variations of the CNM fraction, in fact, even at very small scales. We have developed Fourier techniques also to separate narrow and wide lines in the hyperspectral cubes of H1 data. And we are able to produce a map like that. Forget the galactic plane, we were not able to estimate this, but this map is showing you the CNM fraction, so the amount of mass that is in the CNM, and many clouds are appearing, some that we didn't know about. So this is a new tool for us to understand how cloud is forming. This is the column density of those clouds, and what's interesting is to compare that to CO. So that's the CO map of the galactic plane. So there's almost no CO at high galactic latitude, very little. It's mostly concentrated in the plane and in some clouds close to us. And so when you compare to the CNM, we see a very good correlation, in fact, but also a lot of regions where there is CNM and no molecular gas. So I will pass about this. This is the SMC. This is a halo cloud in the SMC. This is part of the SMC. And what I wanted to show you is this map of that cloud. This cloud is 500 parsecs in size. It's in the halo of this SMC. And what you see here is the fraction of CNM. And the bottom of that cloud is fully CNM. It's totally cold gas now, and probably due to the fact that this gas is entering the halo of the SMC and compressing. What about magnetic fields? So that's my favorite image of the Planck data, showing the relationship between dust, column density, and the orientation of the magnetic field. These are the two imaginary clouds. What I want you to have a look at is this filament. It's a filament that is about 100 parsec in length. It's close to us. It's 270 parsec. It's at a distance of 270 parsec. And the magnetic field is fully aligned with it. It's a structure that is where we see a polarization, dust polarization very well aligned with the structure. If you zoom on it and look at that higher resolution with WISE data, this is that piece of this filament where you see like threads of that structure at small scales. It's a very, very surprising that those structures can be elongated over such long distances in the solar neighborhood and being aligned with the magnetic field. That is telling us something about the dynamics for sure. So we are trying to do numerical simulations with magnetic field and CNM formation. This is an example where you see small clouds being formed into a magnetic, and I don't have time to go through the details of Faraday tomography. This would take me 2 hours. But we have been trying to reproduce from simulation box what we see in the Faraday sky using LOFAR. This is a polarization, maximum polarization intensity in a random piece of sky at high galactic latitude. And by doing synthetic observations of our simulations, we are reproducing something that looks like that is similar to this. And it's telling us that a lot of the electrons that are producing Faraday rotation in the diffuse ISM are in fact coming from the H1, which is a new result. So okay, I know I'm but I want to show something at the end. This is very important. Yeah. Now we want to go to very small scales because we really want to know what the structure of those CNM clouds is. So there's two ways to do this. One is optical scattered light. So this is dust emission. This is dust scattered. It's scattered light, so it's grains that are scattering starlight, and so it's optical. So it's a 1 arcsecond resolution. Those images are fantastic and tell you something about, well, there's many stars, many galaxies, but you get an idea of that, of the structure of the ISM. So this little filament, you can see it, zoom on it. And this is about 200 AU in size, and it's very elongated. So we are really getting into the milliparsec scale with this kind of observation. And the very last thing I want to show, and you want to see this, it's a JWST project led by Josh Peak. And the idea of that is to use Casset, which has, there's a light echo that is propagating in the ISM coming from Casset, so that supernova exploded 350 years ago, but there's still a light echo that is propagating into the ISM, and this light echo is lighting up whatever ISM that is on its way. So it's like doing an MRI of the ISM by having this light that is just propagating. And if you can do that at different times, you're able to reconstruct what the ISM would look like in 3D. And this is what we are doing. And the first observations are coming, and we are observing this thing right now. And so what you see here is really, look, this is 1 parsec. So we are looking at very milliparsec scales of the CNM. We see very, very interesting filamentary structures at the milliparsec scale with these observations and more diffuse clouds. So yeah, this is just a few days of data. So you would see that it's moving a little, and just because we have taken observations at different times. So yeah, this is what we are up to now. It's very exciting, and I think we'll learn a lot about the small scale structure of those clouds. And I'll leave you with my conclusions. Thank you.
Okay, thank you. You said that so the CNM fraction remains pretty constant in our galaxy. Is it something we can check in other spiral galaxies?
Oh, I'd love to. We need to observe, and Eva, please listen. We need to observe nearby galaxies with high spectral resolution to be able to see the CNM line. That's what we need to do. And I don't think we have this data right now. Or maybe little things. Bruce mentioned little things. Maybe there's 1.2 kilometers per second resolution. But we need to have deep observations of nearby galaxies with high spectral resolution in order to do this, yes.
So did you hear that?
Further question. I had a question about the very brief result you touched on about Faraday rotation, and you mentioned that your simulation suggested that the Faraday rotation was dominated by the W and M, and that seems very surprising to me because the warm ionized medium has a much larger volume filling fraction. So is it really the electron density, or is it also the magnetic field strength that's dominating that?
Well, yeah, I didn't have time to go into the details of that. The conclusion is at low frequency, at this low frequency of LOFAR, we see Faraday rotation coming from the thermal electrons that are associated with the H1. That's our claim. With a fraction, ionization fraction of 10 to the minus 4, 10 to the minus 2, which is the typical ionization fraction of the H1. There's enough electron there. There's a lot of H1. There's enough electron in this component to create the amount. Look, the amount of polarization in Kelvin is exact. It's matching totally what we are observing. And this is, so there's, I'm not saying the WIM is not contributing to Faraday rotation. It is contributing to Faraday rotation when we observe external galaxies. This is, but at those frequencies, we are really seeing the last bit of what has been rotated and what is close to us. And this is the interpretation we have now.
I'm sorry, for the sake of time, please talk to the speaker.
Yeah. Thank you.
at the reception. I would like to thank all the speakers of the session again, and then hand over to